I really want to welcome Ranjith Tharayil as our esteemed speaker. Ranjit is an accomplished innovator, author, entrepreneur, and inspirational servant leader. He has been honored with the title as Mentor of Change by NITI Ayog, Govt of India, and was associated with the Association for Computing Machinery as ACM Distinguished Speaker. A lot of things, like a mentor, great thing. Ranjit would be speaking on test driving self-learning systems to continuous delivery, which is a really exciting topic, how to self-learn this. So if you want to know more about Ranjit, you can visit the link below. Okay, so now, so welcome Ranjit, and you can take over the control. You can share your screen. I will unshare my screen now.
Sure. Thank you. I'll just share my screen. And thank you for the lovely introduction.
Yeah, go ahead. Thank you.
So is my screen visible right now?
Yes, Ranjit.
Okay, great. So thank you for joining my talk, and I hope you are having a great retreat. There's a great conference going on, and I think you guys are enjoying and learning at every talk. I was also learning similar to you, and there were some great talks. So thank you for the speakers, organizers, and people who are attending. So I would like to thank each one of you. About myself, thank you for giving that wonderful introduction. A couple of more points. As an entrepreneur, I have three startups. Vidyalayam is one. I think you would have heard that in media already. It's a social startup. The second one is Certify Me Online, and third one is Quadralogics, which I am co-founding. All these three. I also have authored three books. I think you'll find that in my LinkedIn page. So the topic for today is mostly an experiential topic. When I say experiential topic, it's because what I have gained through my little minor experience as a technical coach, trying to build in software craftsmanship as a skill in AI or ML based teams. So it's very experiential and it's very limited to my experience. So my experience might not be as wide as you guys. So pardon me if I'm getting things wrong. But if you feel that there is something that you could take away, I would be most happy. So that's the disclaimer that I would want to give starting the talk. So this is around 2 years ago. I was consulting for a large retail-based client, and this particular client was very big into their new range of products that they wanted to launch. So this, when I say retail-based, is not a pure retailer, but a client that serves large retail clients. I mean, their products are used by large retail clients, giants, in fact, one of the best retail softwares that we have in the market today. And they were trying to build their new class of products, which had a lot of it dependent on a lot of ML based AI systems for a lot of prediction logic, because predictions was something that or AI was something that was widely supposed to use in a lot of problems that would be solved in this particular field. And they had a lot of their new generation products powered by this capability. And I was one part of their team trying to help them build great software craftsmanship skills as a agile technical coach. Okay. So I'm still hands-on. My last commit is just a couple of hours away, so I'm still hands-on. So being a hands-on technical coach, my role was to guide them. And this was interesting when I just joined the team. I was just looking into their code bases and I saw that their coverage was around 92%. And I was pretty much impressed. But looking at the defect counts that they were seeing, it was very high. Their concern that they had raised as a team was that they were talking about continuous delivery. This is 2 years ago, and you would know that at that time, a lot of teams were moving towards continuous delivery. Whereas this product line, they were unable to do a continuous delivery mode So that was something that was concerning them. And that's the reason why they had called me of how do we get their systems to a more CI/CD kind of a mode where they could reach faster to time to market, making sure that quality is not compromised. So I was there. I started looking into the code bases. As usual, code is my field of. I love to see a lot of code. So I ended up seeing, and suddenly I noticed something. Though there were lots of test cases written, most of the test cases the assert was commented. And this was so natural to ask him why are we commenting these asserts? So the development team was a bit shy because they knew that they've been caught red-handed, and they said that Ranjit, please don't discuss this with the management. We would all get because see the management pushes us into this like saying that you need to get into a coverage of 90 plus. And we always strive to do that, and we've tried our best from our heart. But you see that every time, though we do the test correctly, initially it passes, but at some point later down the lane, it becomes a bit flaky and it starts becoming red. And this has screwed up our entire life. We have been working late hours. So the only option we have done is we've tried commenting out. That is the only way we are passing through. And so that's the whole. So I said, okay, then we can't believe our test cases, right? Because see, in the world of continuous delivery, you should trust your test suite. If you don't trust your test suite, then continuous delivery is not even possible. By commenting it out, you are not adding any. I mean, you're taking away that trust further away, because you would still see that there is a lot of defects happening, and your test suites, you're not able to rely on it. So I got down the problem, but I was trying to understand why they were commenting it out. So I said, why can't you correct the test? Why can't you fix the test? He said that, Ranjit, we've been trying our best. We have tried our best. Can you just take a step? So I had this little bit of ego on me. Come on, let's do it out. And I just tried to fix their round of test, made it all green. I said, yeah, look, everything is green now. Why don't we start making sure that we don't comment this out? So they said, okay, but Ranjit, wait and see. And as how they predicted, after a couple of releases, there goes the test being flaky. Now, this was something to be checked on. I mean, I've been working in this space for a pretty long time, and how come the tests are so flaky? Not just one, but many of them hitting one by one. So that's the time I started reflecting on this particular topic, and I got to know that test driving ML-based systems or AI-based system is a bit different from the traditional systems, and that's how this entire talk is molded. So let's try to understand the difference first, because once you understand the difference, then it's easier to understand the solution. So this entire talk is molded upon, first, if you understand the problem, I think you are 50% there. Then I've got a 4-point strategy, which I applied to their code bases, which helped them. I will discuss that also. If it applies to you, you can try it, modify it. It's all up to you. The first thing is trying to understand why an ML based system is different. Okay. In a traditional system, non-ML based system, how do we see? We have assume that you have a system that you're seeing that in blue color, right? You have a function, you have some logic written, you have a lot of ifs and whiles. Your core production of business logic is written in that blue box. What you do is that you provide it an input. Assume that in our case the input is AA, and you know that when you give this input AA to this functional block, the output should be BB. Okay. Now, how do you write it as a test, or how do you automate it using? I've just used Java as a standard. You can assume that this can be replicated in any language. It's language agnostic. So what you do is that you'll write a simple test saying that when when AA is being inputted, BB should be your output. Or you would just say that should return BB when input is AA, and then you would have your test case written. I've just simplified it for the sake of simplicity. You would assert with saying that when you're calling function AA giving input, when you're calling function giving input AA, your output should be BB. Simple, right? Input A, output BB, you assert. If things are not correct, then there is a problem with respect to the function that we are built. The output is not expected as per what we had designed. Okay. So this works out in a traditional system. Now let's understand what happens when we have a ML-based system. Okay. When we have an ML-based system, what is happening is that earlier we had output, okay, that is AA, and we had an input that output was BB, the input was AA, and we had some code which you're seeing in the blue. So the output was dependent upon two parameters in the traditional way, that is the input and the code. Okay. Now, when you change your input, that is, if you change AA to some other value, definitely your output also changes. But based on that, we could write test. Now, what happens when ML is being introduced? Your function, or the way you can represent your output, is no more just dependent on your functional logic. It's because a lot of these functional logic has been written as part of your ML probability models or as data. So whatever you had as your if and while loops earlier, the conditional statements, that all gets diluted into your statistical models, which is there in your machine learning models, could be probability models or anything of that sort. And now what is happening is that now your output, that is your output of your system, is dependent upon three parameters. It depends upon your input, it depends upon your code, and it also depends upon the model. And you can see that a lot of things that were earlier only there in the code has now moved to the model also. So now there are three variables. Okay. And now what happens is that in self-learning systems, this data, that is the model, keeps on changing. Every second it keeps on changing. Every time there is an input, it keeps on learning. It's a self-learning system. So now what happens when you write a test like what we wrote earlier, like say that when input is AA, the output is BB. Maybe it might work for the first time, but after some time, when you see that the machine learns, then the output might change a little bit. Instead of BB, it might give BC. Now what happens to your test? Your test fails. Now, this is not a problem with the system. The system might be perfect because it is supposed to learn and correct it. But what happens is the way we wrote the test is incorrect. The reason why we say that is that this kind of writing the test, the way in which we wrote the test, is called a state test. We are trying to check the state of a system. Like we give an input and we assume that the state of the system is changed and we check for the output. And the problem over here is that since we write the test initially, right, and the statistical models keep on updating gradually. Maybe initially it is a green that you will get, but say down the lane 2 or 3 weeks, you will see that the models have changed, and based on that, your output is changing. Instead of BB, you're getting a BC. And this means that your test becomes flaky. Now just assume that you have thousands of these tests there, and you see that 25% of them have started becoming flaky. How much trust do you give onto your test automation suite? And that you will not even have trust to go to continuous delivery, because for continuous delivery you have to have a solid automation suite. That's the only way that you can get to that state, right? So this was the problem that we were dealing with. There were three variables compared to two variables. The third variable, which was the model or the data, the probability model, was continuously changing, and because of that your output was changing, and we were not able to write tests, like automated tests, like how we used to write before. Okay. So I'm just summarizing the problem statement. So this becomes 50% of knowledge, I would say. If you know the problem, then you can apply your own solution. So test driving was difficult for self-learning systems. Okay. Output of the system dependent on the statistical model also. It is not dependent on just the code that we write, but it's also dependent on the model that we are. And that model keeps on changing. And because of that, the test becomes flaky. Now, the question that we're trying to answer here, this is the second half of it, is how do we enable continuous delivery for an AI system? Okay. What should be our strategy? Now, there's a 4-point strategy. And as I told you, this is the way we solved it over there. Doesn't mean that this is the only way. This is one of the ways that we tried it, and you can try it within your systems also. The first thing is that if you look at any AI based systems, right, you can think about it as or you can segregate it or virtually or mentally map it into at least 3 subsystems. Okay. What you're seeing, that 3 subsystems, is within the dotted box. You're seeing a dotted box, right? It's within that. The first one is the business logic binding the AI system. Now, not all the systems just have AI, right? They'll have a lot of other business logic, and AI is a lot more of as an enabler to help certain things, maybe a risk calculator, a prediction model, or a predictor, or something of that sort. AI is used to help in some business decisions, right? So now there would be some code that is binding the AI with the business logic. So that is what is showed in yellow color. So that is one set of functionalities. Why are we segregating is because we need to handle, or we need to approach testing differently for these three categories. The second one is you would need a lot of algorithms for or standard libraries that are already there. So maybe you are using Python, or you're using R, or you might be using any other libraries that are already there. But at the end of the day, if the library is also faulty or it doesn't work on your environment, sometimes some of these calculations are done on your mobile environment. So we need to make sure that they are also correct. Some of the times I've seen that we do a lot of, in order to make it faster, right? We have aspects like caching built in, customized caching, so that calculations are done much faster, so that we don't need to recalculate. And there's a lot of custom logic just to handle this algo module. So I call it standard algorithms plus data structures. Because when you're talking about typically you use graph type of data structures, and the amount of code that goes into just maintaining these data structures is huge, right? So that's a separate part that is in the blue color. Then the third one is the most important one. That's the model itself. When you say model, it could be probability models. It's the model that is the trained models that we are using in AI. And that could be in a database, or it could be just flat files. It is something that it could be probability models. It's something that you have something more tangible, persistent data that is available, which keeps on changing also. And apart from this, you have the other business logic that is in the green color that you're seeing on top of the dotted boxes. And this green color is the rest of the code that you can use your standard strategy for testing. Now, once you've carved out your system, now you know that these three different subsystems you have carved out. Now we're going to apply three different strategies for testing these three. And that's the reason why this what you call refactoring it into these three is very important. So the first step would be that if your source code, or the way we have written code, is totally mangled and is not separated out in these three categories, then that is a good idea to refactor it and make sure that these boundaries are well marked and demarcated. Okay, so that is the first step, and that is the first strategy that you need to apply. Now, in order to understand this solution, right, it's very difficult to just, it's like learning swimming with a theory class. So what I've tried to do is that with this short amount of time, I'm going to take you through an example. Now you will have a little bit more understanding. In order to get really into it, you need to get into the pool and learn swimming. Now I'm just trying to show you how to swim by me entering into the pool. So I'm just taking a small example. I know that this might not be sufficing, but you'll get the crux of it. And I think later on we could discuss in the Q&A on more details about it. So what I'm trying to do is that assume that you want to build a world-class prediction system. Just taking a very simple example, because everybody would know what is a prediction system is. Like you have your mobiles. When you type on your chat, you want your mobile, your keyboard predicts what word you're going to use, right? So that's a simple prediction system. Now let's assume that we want to build that example. You can extrapolate it to your own context. It still is would be valid. Now for building this, I'm just going to introduce a few technical terms. If you don't understand, it's perfectly fine, but it's very simple. You need there are two concepts that I would explain. One is a unigram model. Now what is a unigram model? I'm just explaining this so that you understand the integrities of what we're going to discuss later on. So a unigram model is just a simple, assume that you have a dictionary, okay? And now or you have a textbook that you have, okay? Just assume that you have your favorite textbook. Now you're going to go through each one of your words in the textbook, and you're going to note the occurrences of each word. Now certain words might occur at a very high frequency compared to others. And then you note down the probability. Maybe a particular word has got more occurrences, maybe a certain occurrences. So based on this, you create a table, and that's called a unigram table. Okay. Now, similarly to that, you can create a bigram table, because whenever we use sentences, right, in a textbook, we use two words together. For example, hello world or good morning. The chances that you say good morning might be much higher than good something else. So now you look at the probability of occurrence of two words together. And then you say that, good morning has got a higher preference than some other two-letter word. And you build a probability model that is called your bigram model. Okay. Don't get too much detail into, just assume that these are two tables. And this is your model in our example that we're going to take, the model that we defined earlier, right? Now assume that this is something that we want to achieve. This is your patented world-class prediction system. And whenever somebody is typing a word, a single word, he started typing, say that he started typing a particular letter, say for in this particular, where should we celebrate your promote, is typing in between that word. It's not hit a space. It goes to the unigram model to check whether it is the, whether what should be the right word. In this case, promotion is the topmost word. You'll see that on the top of the list, right? So promote would come as the better candidate as prediction. Now there is another rule also. Whenever he types a space bar and then he looks for a word, it goes to the bigram model. Now just assume this sample business case. I'm not complicating it over. There are these two rules that needs to there, and you see these two models are used. Now if you've not understood this, you can just park it and just say that there is some business logic needs to be developed. You can just consider it in that state. Okay. Now let's assume, where does these systems, the business logic binding the AI system, what does it do? It needs to depend on whether I should call the unigram model. If it is in between a word, that is within a word, I should call the unigram model. If I've hit space, it should call the bigram model. This small logic is what we call it as the business logic binding the AI. Now, the second part, the algorithms, you might need, for example, to store this, you might need a hash table, a list, so that hashing is much better because you might need to recover things faster, right? So that is the algorithm that we are talking about. You might want to use caches because whenever a particular word is being hit more number of times, you want to probably store it so that your lookup is much faster. Because we're talking about tons and tons of words, right? In the real world, I've heard that Google keeps 5-gram models, and you can assume that number of lists in the 5-gram model will be pretty huge. So let's not talk about that. So that is the part that comes in algorithm. The model is something that what we earlier explained. The bigram model is a probability model which just lists down the occurrences of the letter, and higher the probability, the top they would be. It's an ordered list. So now you know how to separate or segregate using this example, right? Now you can think about your own context and see how these three subsystems can be segregated, and you should have clear demarcations on it. Now let's assume, now let's go one by one. Now, how do you test the yellow one? That is the business logic binding the AI system. Okay. Now, what we typically do is that there is something as we need to predict, and whenever there is a space, you need to go to your bigram model, or if there is no space, you need to continue to look into your unigram model. This is a small if condition. If you look into the code, it's an if condition. If there is a space, then you go to bigram. If not, you go to unigram. Now, how do you model it as a test? Now, assume that you write a test like this. Okay. Should return should. Okay. Should is just saying that whenever we write a test, we always start with should, right? I just wrote it so that we could have some fun. Should return should. Assert equals whenever you're starting with the word where, the sentence that we are trying to predict is where, and the user is typing sh. Okay. He or she is not is wanting to type the next letter and is trying to get a prediction. He or she is only typed where sh, and it's trying to look into, it should look into the unigram model because it's in between a word, there's no space. And ideally it should return should, assuming that this is the most probable word. But this is a state testing. Do you think this will work in ML based systems? Maybe it might work. Your first word might be probable word might be should, but assume that when it was self-learning and maybe you've been typing a lot and you've been watching Sheldon or the Big Bang Theory a lot, and you talk about Sheldon a lot, suddenly your probability changes that instead of should, your probability changes to Sheldon. So maybe after some time, because it's self-learning from your chat logs and various things, it's learning and it's understood that Sheldon is more probable, then this particular test we are trying is going to fail. Because when you're going to look up where sh, your system is going to return Sheldon. Earlier it used to return should, earlier it used to pass, but now it used to fail. So this particular kind of testing will not work, and that's what we explained earlier. So how do you approach this problem is a concept called as interaction testing. Now, in the case of interaction testing, you don't test the actual state. What you are going to check is, in fact, you can use mocking libraries to do interaction testing. And I'm not going to go in details about mocking libraries, but what you do is that you're checking the behavior. You're checking the arrows that is written in black color. Whether I'm calling the right function, I'm not checking whether it is returning the right value because it's going to change. But in case there is a space, in this particular case, it should look for the unigram model instead of the bigram model. Is it calling the right unigram model function? That is the behavior test that I am implementing. And this is an example of how is it. I can't go into the detail because it'll take a lot of time and discussion. But this is how you write an interaction test, not integration test, interaction test. Okay. Now this will pass irrespective of the model. Okay. Now this is checking whether it is calling the right function, and it would check irrespective of the model, whether it is Sheldon's or something else, Shelly or something else. Even it comes back, it would pass. So summarizing, at this particular layer, that is the yellow layer, you need to focus more on interaction and behaviors. You need to avoid state testing. And in this particular case, you will have the opportunity to mock the entire algo library. Algo libraries are pretty much heavy duty, right? So you can just mock it and use a mocking framework to entirely mock it so that you don't need to instantiate it. So it becomes much faster. You can see that a lot of these testings can be written at a unit level. Okay. Now the second one is how do you test your data structures and algorithm layer? That is the central part that we want to check. So we earlier studied how do we check the business logic layer that is interacting with our AI. Now there is a lot of algorithms that is required, data structures aspects that is required for loading the model and things like that. How do you test that? Now, what we know that in our previous discussion, our output is a parameter of input, code, and model. Now, what are we going to do is that we're going to create a very simple model. In this particular case, maybe we create a small dictionary of bigrams and unigram models and always keep it as a constant. We don't change it, only in the text context. Only in the test context, we're going to use this. And because the model is constant and it's not changing or evolving, you know what is the output. Now, because the input and the code and the model is constant, what happens is that the equation becomes like almost like how we had it earlier. Now you should assume that in this particular, whenever you're doing such kind of testing, the model, when you're loading for this test context, you should inject the model in such a way that you're using always the same model, and it should be simple enough so that you can write the test, not so complex. Why is I'm saying simple is because your test will also be faster, because if you're loading a 1 million or a 100 million record table, it might not work, rather than just use a 2000 record table. So you're just faking the model in other ways. Okay. And you're testing whether your algorithm is working, because your algorithm should work. If it's working here, then the chances that it will work there also is very high, so that you're testing it with a smaller model, with a constant model. Okay. So what key things is that here you can use state testing because your model is constant. So you can use some amount of state testing over here. You can also use interaction testing, no doubt in that. Interaction testing also, but you use your traditional way, only that you keep your model constant. You have to fake your bigram and unigram tables. That is the thing that earlier you need to mock. Here you need to fake your bigram models. Okay. Now the third one and the last one to be discussed is how do you test the model itself? Now the model is where the crux lies, right? The entire probability model, you can assume that. And we understood how to test the business layer, how to test the in-between algorithms. How do you test the model itself in a continuous delivery mode? So what I'll just, though this is a larger topic of discussion, I'll just give you the crux of it. Now you would have a truth set. When I say a truth set, is a set that assume that you have some specialist in a particular field. Say that if you're insurance guys and you're looking at a particular application, or just looking at an image and trying to identify it is what it is, you have a truth set built by a set of people, okay, who you trust. Okay, if it is in a medical imaging system, you might have doctors doing this, and this truth set is not to be used for training. Okay, and whenever you run your test, or whenever you write your code, you want to make sure that you test it with the truth set. And there is something called as the dice coefficient, because not always your test would pass over here, because it's self-learning. Even what I say might be if assume that I'm trying to understand benign tumors, what I say is benign tumor might be different from another context, right? So there would be some amount of tolerances, and that tolerance is something that you can configure. But the crux of it is that there should not be too much of a variance. So then if there are too much of a variance, then that will be flagged and your continuous build would fail. But if the variance is in limited period, then it passes. I think this one is something that you would always somewhere see, right? Certain AI systems are not allowing blacks to apply for a loan. Such test and all gets captured in this in this test. Such things can be tested and made sure that such code doesn't get outputted. Okay. Now, just to summarize this entire thing, we understood the problem, and we understood that there's a 4 strategy that we need to use. First is refactoring. We understood the 3 subsystems, and we understood each subsystem has a different strategy to refactor. So I'll just park for any Q&A if there is any Q&A.
Thanks, Ranjith. We haven't received anything in the Slido, but anyone wants to just have a one question, we can take it up. One question. You can. Does anyone have any question, or we can? Yeah. So then I think it was a great session actually. Then
thank you.
It was like I was engrossed in this session, to be very frank. So I really want to thank you for your great talk and a great insight, because and sharing your experience, that will really help. So
Sure.
Yeah, thank you.